Welcome to Physics, Unit 2, Lesson 2, Friction and Forces, and I always like to add fun. Okay, the purpose of this lesson is to define for you various types of forces that are involved in motion, really of everyday objects, and in particular friction, and also to look at free body diagrams which show the forces and the direction on any given set of objects. Okay, let's first define what a force is. Okay, a force is a push or a pull on an object. And there's two classifications of forces. There are balanced forces and there are unbalanced forces. Okay, well, the picture that we are showing here is a tug-of-war game. And if this tug-of-war game is perfectly, wonderfully matched, you will have a force. On this team is pulling in this direction. This team is pulling in this direction, and they're totally equal. So equal in size, opposite in direction is what a balanced force is. If that happens, there can be no accelerated motion. In this case, it's probably not any motion at all. They're pulling one direction, they're opposing that pull in the other direction. Forces of balance, equal in size, opposite in direction, no accelerated motion occurs. Now, let's say that, a ringer, a big guy, comes over on this side. Woman, big guy, and he's going to grab on and help this team. Now you might have a much greater force in that direction, still the same force in this direction. Well, when that happens, this team on the right is going to win, and the motion is going to start going in this direction. And that is called an unbalanced force. Unbalanced forces are when you have more force in one direction than the other. There is another word for unbalanced force, and we call that net force. Okay? So net force equals unbalanced force. More force in one direction than another. Here's another example of a balanced force. The truck is staying still because you have equal forces on either side, and the truck is staying still. Now, if one side increases the force, let's say doubles that force on the other, then that truck now is going to move in the direction of the net force. So if we subtract the forces, maybe the net force might only be about this big, but it's still enough to move that truck in that direction. Now that becomes an unbalanced or a net force. The net force is what can cause the accelerated motion. Now, another type of force that we often don't consider a force is weight. Okay? And weight is the force due to gravity. So that's what it is. It's the measure of the gravitational force between any two objects. And if we had to actually calculate what the weight is, sometimes I'll use F sub W to equal weight, or oftentimes it's written as F sub G because it's the force due to gravity. Well, what that equals, that weight equals the mass of any object times the acceleration due to gravity. So if you're looking for a weight, you take your mass, and it has to be in kilograms for using this, times your acceleration of gravity. That would be 9.8 meters per second squared. And that would give you the weight of any object on the earth in newtons. So the unit is newtons, named after Sir Isaac Newton. Now, back to my balanced force picture up here. They also, though, have weight that they put on the ground. So they're able then to have a little bit of traction. We're going to get into friction in a minute, but all of their bodies are expressing always a weight downward due to gravity. So here is showing that the weight of the girl sitting on the chair, and that is being counteracted, and we'll get into this a little bit more with Newton's laws, with the chair pushing up on her to be in equilibrium. But weight of any object is the mass times gravity, and it is in newtons, and is always acting downward. So that's one force that exists in every single object, no matter what the object is. If it's something falling down, let's say you have a ball falling down from the air, there's my ball. The force that will be on that is its weight is always there. We can either call that F sub W or F sub G. That's the weight is one of the forces that does always exist on any object. One of the things that opposes the objects is the upward force of air, and we label this air resistance. Okay, so air resistance is equal to the force of air exerted upward on a falling object. Now, we also will have air resistance in horizontally, and we call that drag, and we'll get into that as well. Okay, there we go. Now let's look at the two skydivers I have here. I'll call this Skydiver 1 and Skydiver 2. Well, Skydiver 1 jumps out of the airplane. Okay, the F sub G on both of them is always there. Okay, but a Skydiver 1 jumps out and accelerates downward. The net force due to gravity is down. Well, when she puts her chute up, okay, air molecules are gaining under that parachute, and it's trying to slow the skydiver down. When those air molecules now have equaled the weight, she now has reached terminal velocity. Terminal velocity is the fastest velocity a falling object reaches, and it occurs when the force of gravity, their weight, equals the force due to air resistance, and we often write that as an R. Now, parachute number 2 here, he is a little bigger than number 1. And so it's going to take a lot more air molecules to equal his weight. So this person is going to have a higher terminal velocity, but still will reach terminal velocity, just not as quickly. Okay? Still will reach terminal velocity. If your parachute doesn't open, or before you open it, you will reach terminal velocity because you are falling through the air. Your body, right here, your body, either one, it will gain enough air molecules underneath it to equal your weight, and that is terminal velocity is reached. However, that terminal velocity might be something like 110 to 120 miles per hour, and you don't want to hit the ground with that. So the parachutes help you to achieve a much smaller terminal velocity, maybe 10 miles per hour, that you can land safely on the ground. Now over here, this picture is showing an elephant and a feather going off of a building. Well, the feather almost immediately has an upward force of air equaling its downward weight almost immediately, and terminal velocity very, very quickly. The elephant, I'm afraid, will take a long time to reach terminal velocity and probably won't be hitting the ground at terminal velocity at all because not enough time for his weight to be equaled. Well, air resistance is a type of friction, and since friction is so important and so prevalent in our everyday life, let's define it and go through it. Friction is the opposing force between two surfaces in contact. Okay? Well, let's look at our picture over here. We have on the ice, this poor polar bear is slipping because if he's trying to walk this way, there's just not enough friction to keep him upright. So slips and he's falling. Okay? Friction, think about it. If you're walking down the road or you're trying to drive on the road and that is icy, like in the wintertime, it's very difficult to walk and drive in icy conditions because you don't have enough friction at all. All right? There are two types of friction. We call static friction, and we have what's called rolling friction. Okay? Static friction always requires more force than rolling, meaning it takes more force to get an object in motion, static meaning stopped, stationary. So it takes more force to overcome static friction than it does rolling friction. And we'll look at some chart on the next slide. I'd like to draw your attention to this picture here because this is really a free body diagram that we're going to get into more. And so let's look at all the forces that are involved in pulling this little truck on wheels. Okay, so the pulling force we're going to call the applied force. The way I like to make it from the center, when I'm going to make it nice and big, it'd be nice if I could draw a straight line, but that's the weight, Fg, and the rolling resistance, we're going to call that Ff, force due to friction, that's what we use, and then there is a force that is upwards, and that is my Fn, my normal force. Now a normal force is a perpendicular force between an object in the surface. That's what the normal, it's the surface supporting that object, okay? Whenever you're on a level surface, that normal force is equal and opposite to the weight. So we do know what it is. The normal force is a perpendicular force. So sometimes I'll write the normal force as F, a perpendicular sign, because it's the perpendicular force between two surfaces. And so if this is my surface here, or I guess my wheels of my surface, okay, that normal force has to be perpendicular to that, okay? Now, of course, I love equations, so there is an equation for finding the force of friction. And to find the force of friction, you need to know the coefficient of friction, mu, and I'll explain this in just a second, times the normal force, okay? So what this symbol is a Greek symbol, and it's pronounced mu, mu, and all mu is a proportion between two surfaces in contact, okay? And there's values, set values for mu. And if they get too high, you have lots and lots of friction. If they get too low, you have very little friction. And we'll look at the table in the next slide. Well, as promised, here is a coefficient of friction table. So coefficient, there you go, not the easiest word to spell, of friction table that I got from a physics journal. Now, mu sub f, S means the static, coefficient of static friction, mu sub k, that k is often used for kinetic friction, kinetic being motion. And we'll get into kinetic energy, which is the energy of motion, a little bit later on in the physics course. But, so this is the rolling, so this table here is the rolling, and this table here is the static. All right, let's just look at some of these. All right, things that you might use on a regular basis. Rubber on concrete. So this is your rubber tire on dry concrete, has a static coefficient of 1. 1's the highest you can have. So that's pretty good. I'm pretty safe driving. I'm pretty safe having my teenager drive her car in nice dry conditions. All right, that's just to get going. But then once she's going, it drops to 0.8, still pretty high. Still pretty high, okay? Very comfortable. Now watch what happens. Rubber on wet concrete, just to get the car moving, drops way down to 0.3, very low, and then 0.25 once you're in motion. Well, now I'm going to be a little bit more nervous driving in wet conditions because it's going to need a longer stopping distance. Really, that's what these can help you out with. You cannot stop as quickly if your coefficient goes down below the 0.5 mark. So we have like wood on wood here, glass on glass. If you ever try to separate two glasses, it's very difficult. It does drop once you get them moving though. And then, we have, ice on ice, very, very, very small friction. So ice is very little. We have wood on wet snow or wood on dry snow. You can see how low some of these values are when there's very little friction on that support. I thought this one was good. These synovial joints in humans have very low. That's one of the things that we are very good, very efficient in our joints. We have that synovial fluid that helps and to really reduce the friction so that we can move and do all kinds of activities. Okay, let's review all the key forces that we've had. All right, so we had applied force, those forces that are put on objects. So we have applied forces, and that is F sub A. If we're using a rope or some kind of string that can get tight, we call that tension. So that's the applied force due to tension, and that's F sub T. We have friction involved, whether it's static or rolling, and that's F sub F. We have weight. Any object, weight is F sub G. We have normal force, which is the perpendicular force that a surface exerts upward on an object, F sub N. And we do have air resistance too. That could be in a problem. So air resistance is F sub R. And now the next short video I'm going to make, we're going to look at free body diagrams and how to draw them effectively using these forces.